Alright, in this video we're going to be talking about the electric field strength and the electric field potential. But before we go to that, we need to understand first the concept of electric field. Now, the electric field is a region or space where the effect or the impact of an electric force is felt. Now, to describe the field around a point charge, we make use of electric field lines or the electric lines of force. Now, every charge, be it a positive charge or negative charge, will create a field around it. This is a point positive charge, and this is what the field around it looks like. To describe the field around a charge, we make use of electric lines of force. Now, the electric lines of force show us the direction of the field. You can see this is a positive charge, and the lines of force are pointing outwards. All right, all these arrows here are pointing outwards. So we'll say the lines of force around a point positive charge is radially outward. So this is what the field around a positive charge looks like. All right, so the field is simply the region or space where the effect or the impact of an electric force can be felt. So this is the region around this charge. In this region, the impact or the effect of an electric force can be felt. So say this region is the field of this charge. The same thing here. This is the field created by this charge. All right, and around this region, the impact or the effects of an electric force can be felt. So we'll call it the electric field around this charge. Alright, so the electric field, like we said here, is the region or space where the effect or impact of an electric force can be felt. And the field around a point positive charge, do not forget, is radially outward. You have the lines pointing out. Whereas the field around a point negative charge is radially inward. You have the lines of force pointing inwards. Now, talking about the electric field intensity. The electric field intensity is also known as the electric field strength. Now here it says electric field intensity is a force experienced by a unit charge when placed in an electric field. It is also called the electric field strength. Now its symbol is E. E is the symbol for electric field strength, and then it is measured in Newton per coulomb. All right, I'll take our definition again. It says the electric field strength is the force experienced by a unit charge when placed in an electric field. That force a unit charge experiences when placed in an electric field is what we call the electric field strength. And mathematically, electric field strength E, do not forget the symbol for electric field strength is E. Mathematically, we have electric field strength E equals force all over charge. All right, this is the equation for calculating the electric field strength. We have E equals F over Q, where F is the electric force experienced by that charge, and then Q is the magnitude of the charge. Now, this equation can be simplified to give us another very important equation, which is very important as long as calculation concerning electric field intensity is concerned. And what's that equation? From Coulomb's law, we have that the force experienced between two charges, Q1 and Q2, is given as F equals KQ1 Q2 all over R squared. All right, so let this be that force a charge being placed in an electric field is going to experience. So rather than writing E equals F over Q, we can replace this F with KQ1 Q2 all over R squared. So in that case, our equation becomes E equals KQ1 Q2 all over R squared divided by Q. All right, where the whole of this is our F. All right, so we have E equals F divided by Q. E equals F divided by Q. Now this can further be simplified, and then we are going to have E equals KQ1 Q2 all over R squared. We'll change division to multiplication, and then we'll take the inverse of this. This Q over 1, we'll take the inverse, and it becomes times 1 over Q. All right, if we simplify further, we're going to have this Q cancelling out one of these. So in that case, we'll be left with just one Q. So our equation for electric field strength or electric field intensity will be E equals KQ all over R squared. So this is another very important equation as long as calculation involving electric field intensity or electric field strength is concerned. So you're either working with this or you work with this. It all depends on the question you're given. So if you're given a question that involves just force and charge, you go with this. But if you're given a question where they gave you distance and they gave you the magnitude of the charge, you have to go with this equation. Now we are going to look at some practice problems where we see the applications of these equations. Now looking at this question here, it says calculate the electric field intensity due to a 5 times 10 raised power minus 16 coulomb charge. So we have the magnitude of our charge to be 5 times 10 raised power of minus 16 coulombs at a point 5 millimeters from the charge. So now they gave us distance, which is 5 millimeter from the charge. All right, so they say calculate the electric field intensity. So we are looking for E, and these are the parameters we're given. Now remember, when it comes to calculating electric field intensity, we have two equations. E equals force over charge, or E equals KQ all over R squared. From the look of things, we have to go with this second one since we are looking at distance and charge. We have to go with this equation. We cannot use this because they did not give us the magnitude of the force. All right, so this is the equation we are going to use. But before we use this equation, we need to ensure that our units are in their standard form. All right, so here we have distance given to us in millimeter. We must make sure the distance is in meter. Even if they give you distance in centimeter, ensure you convert it from centimeter to meter. So how do you convert from millimeter to meter? Milli here is a prefix and it means 10 raised to power minus 3. So R equals 5 millimeter can be written as R equals 5 times 10 raised to power of minus 3 meter. So this is our distance. So at this point, we can now plug in our values and get our answer for electric field intensity. So moving on, we are going to have E equals, now K is a constant. All right, sorry I didn't mention it earlier, but K is a constant and K is always equal to 9 times 10 raised to power 9 Newton meter squared per coulomb squared. All right, it is a constant. All right, so from here we're going to have E equals, rather than writing K, we write 9 times 10 raised to power 9 times Q. Q was given to us here. That's the magnitude of the charge. We have 5 times 10 raised to the power of minus 16 all over the distance. The distance was also given to us. We have 5 times 10 raised to the power minus 3 meter. So we have 5 times 10 raised to the power of minus 3. All right. Now distance squared. So we have this squared, and that is going to give us the magnitude of the charge equals, we'll just use our calculator to simplify this and then we get our final answer. All right, so from our calculator, our final answer here is going to be 0.18. All right, do not forget the unit for electric field intensity or electric field strength is Newton per coulomb. So our answer here will be 0.18 Newton per coulomb. Now our next question here says, what is the electric field intensity on a charge? So they give us magnitude of charge to be 9.6 times 10 raised to the power of minus 8 coulomb. All right, onto which an electrostatic force of, they give us the force to be 6 times 10 raised to the power of minus 5 Newton is exerted. So they gave us force and charge for this question, and then they're asking us to calculate the electric field intensity. Electric field intensity. Now for this question, we're looking at the relationship between force and charge. So the equation to go with for calculating electric field intensity is electric field intensity equals force all over charge. What is the magnitude of the force in this question? We have 6 times 10 raised to the power minus 5. So we have 6 times 10 raised to the power minus 5 all over the charge given to us is 9.6 times 10 raised to the power of minus 8. So that will give us electric field intensity to be equal to, we use our calculator here, and we have for the numerator, we have 6 times 10 to the power of minus 5 divided by, you can put your numerator in brackets, they say divided by the denominator, you also put it in brackets, 9.6 times 10 raised to the power of minus 8. All right, and that will give us 625. So this is the magnitude of the electric field intensity or the electric field strength. And what's the unit again? We have Newton per coulomb. So this is our answer here. All right, from this question, it says 2-point charges, positive Q and positive 4Q, are separated by a distance of 3 meters. All right, so we have positive Q and another charge, positive 4Q. All right, they said they are separated by a distance of 3 meters. So let's say the distance of separation between them is 3 meters. That's what we have here. From here to here is 3 meters. You see, at what point on the line between the charges is the electric field equal to 0? So now we do not know the point where the electric field is 0 on this line, but let's just label it here. We'll say let this be that point where the electric field is 0. So that point, we can label it as X. So say at point X, electric field of this charge is 0. At point X, electric field of this other charge is equal to 0. So it simply means the electric field of these two charges will be equal at this point because they are both equal to 0. So now let's get the value of the individual electric field. If we want to look at the electric field of this positive Q charge, we say for positive Q charge, our electric field will be equal to, do not forget the relationship between electric field and distance is electric field equals kq over r squared. Electric field is the same thing as electric field intensity or electric field strength. So whenever you hear the word electric field, they say calculate the electric field, they are talking about electric field intensity or electric field strength. So we know that electric field in relation to distance, this is the formula. Now I want to get the electric field of this charge with respect to this distance. All right, so the electric field now will be equal to K, which is a constant, times positive Q charge, which is still the same thing as Q. So we have Q all over the distance of this charge to this point. Remember, we said this point is labeled as X. So if we are moving from this point, we're going to be increasing, and then we'll get to this point X. We'll keep on increasing, and then we'll get to 3 meters. All right, so the distance of this charge to this point is X. So we have E equals KQ all over X. Don't forget the distance is squared. So the distance from here to here being X will also be squared. All right, so this is the electric field of this charge at this point. So now let's go to this other charge here. We have that for positive 4Q charge, again, the electric field at this point is 0 for this charge. All right, so now let's try to get the electric field. Electric field for this charge will be equal to K times positive 4Q. So we have times 4Q. All right, positive 4Q is still the same thing as 4Q. All right, so we have K times 4Q all over the distance. What's the distance of this charge to this point? Now we know that from here to here is X. From here to here, what's the value? Remember, we are moving from this point here. We'll keep on increasing. So this is like our 0 point. We'll increase, keep on increasing, we'll get to X, and then we'll keep on increasing, we'll get to 3. All right, so if from here to here is X, from this X now to this point, what's going to be the value? Do not forget, from here to here is 3. From positive Q to positive 4Q is 3, and from here to here is X. So from here to here is going to be 3, which is the total, minus this distance X. So it simply means this distance here, all right, is going to be 3 minus X. 3 minus X. So the distance we are going to use for this charge here plus 4Q is going to be 3 minus X. All right, now do not forget the distance is squared, so we'll say 3 minus X all squared. So this is our value. Now if we simplify further, we're going to have that the electric field strength for positive 4q charge is going to be E equals, we have K times 4q, that will give us 4kq all over. Now we need to expand this bracket. This is 3 minus x all squared. So expand this, we just take this first value, we square it, 3 squared, that will give us 9. Then we'll say 3 times minus x, then times minus 2. 3 times minus x, that will give us minus 3x. Minus 3x times 2, that will give us minus 6x. Then we'll have negative x all squared, that will give us plus x squared. Alright, so this is a shortcut to expanding this. Alright, you can also use the normal method, which has to do with writing this 3 minus x in two brackets and then expanding. Alright, but we can go with this. So this is the value we're going to get for the electric field intensity for this charge. Now, do not forget, both of them, what we just calculated is the electric field at this point for both charges. Now, the electric field at this point for both charges is equal because both of them will have electric field to be equal to 0. Alright, remember they said at what point on the line between the charges is the electric field equal to 0. We don't know the point, so we label it as x. So at point x, both charges will have electric field to be 0. In other words, both charges will have electric field to be equal. Now, since both charges at point x are equal, we can simply equate the electric field of this with the electric field of this. Alright, so since both of them have electric field to be equal, we can simply say the whole of this is also equal to the whole of this, and then we'll simplify and get our answer. So let's forge ahead. We are going to have, for positive q charge, the electric field is kq over x squared. So we have kq all over x squared equals, for this guy, we have 4kq all over 9 minus 6x plus x squared. All right. Do not forget, the reason why we are equating the both of them together is because electric field for this charge at this point, all right, electric field for this charge at this point is 0. Electric field for this charge at this point is also 0. So since both of them have electric field to be 0, it simply means both of them at this point have their electric field to be equal. All right, so it simply means electric field of this and electric field of this at points x are equal to each other. So since they're equal, we equate this with this, and then we simplify. All right, so moving on, from what we have here, we have kq appearing on both sides of the equation and as numerator. So since they are appearing on both sides and they are appearing as numerator, we can simply cancel out. So k will cancel k, q will cancel q, and here we're going to be left with 1. All right, here we're going to be having 4 times 1, which is 4. All right, but we cannot cancel out x squared here because this is a separate term. All right, because of this positive sign. So we cannot just cancel them out. We have to simplify, all right, to get our answer. Here we can easily cancel out because this has to do with multiplication. 4kq is 4 times k times q. This is k times q. So whenever it has to do with multiplication, you can just cancel out. But whenever there is an addition sign or a subtraction sign, don't just cancel out like that. Try to cross multiply and take like terms and simplify, because this guy is standing as a separate term, unlike this. All right, so now we can continue, and then we're going to have, this is 1 over x squared. We're left with 1 all over x squared equals 4 times 1. This is 4 all over 9 minus 6x plus x squared. All right, now if we cross multiply, we're going to have 4 times x squared, which is 4x squared, 9 minus 6s plus s squared times 1. That will give us, we're going to have equals 9 minus 6x plus x squared. The whole of this times 1 is still the same thing. All right, so this is what we're going to have here. Now we can take like terms and simplify, or we can simply move everything to one side of the equation and equate to 0 and solve our quadratic equation. So if we do that, we're going to have 4x squared. All right, this positive x squared, we move it to this other side, it becomes minus x squared. All right, and then we have minus 6x, we move it to the other side, it becomes plus 6x. We have positive 9, we move it to the other side, it becomes minus 9. So at the end of the day, we'll move everything to this side of the equation, so we're going to be left with equal to 0 because there will be nothing left on this side of the equation. So if we simplify further, we're going to have 4x squared minus 3x minus x squared rather. That's 4x squared minus 1x squared. So we're going to have, this is going to give us 3x squared. All right, we have plus 6x minus 9 equals 0. So try to simplify this quadratic equation to get our answer. Now at this point, we're going to solve the resulting quadratic equation using factorization method. Now before we go on to use factorization method, we'll try to simplify this equation. We have 3, 6, 9. There's a common factor, so we can divide all through by the common factor, which in this case is 3. We can break this down. All right, so divide all through by 3. This is going to give us 3x squared all over 3 plus 6x all over 3 minus 9 all over 3 equals 0 all over 3. So 3 will cancel 3. You're going to be left with x squared plus 6 divided by 3. That will give us 2x minus 9 over 3. That will give us minus 3 equals 0 over 3, which is 0. All right. So moving on, we're going to have x squared plus 2x minus 3 equals 0. So to solve this quadratic equation here, we'll now use our factorization method. And by factorization method, we need two numbers that we will multiply. We're going to get minus 3. And then when we add them up, we're going to get positive 2. So what are those two numbers that we can go with? So you can pause this video and think if you can come up with any two numbers that when we multiply, we have minus 3. And when we add them up, we get 2. Now two numbers which you can work with here are minus 1 and plus 3. Alright, so since we are working with minus 1 and plus 3, we want to replace positive 2x with minus 1 and plus 3. We're going to attach x to minus 1 and plus 3. So that's going to give us x squared. Rather than writing positive 2x, we write minus 1x, which is simply minus x, and then plus. Rather than writing 3, all right, we write plus 3x. So minus x plus 3x gives us positive 2x. So the whole of this is being replaced by this. Then we write minus 3 equals 0. All right, so group this and then we take the common factor. So we have x squared minus x. This would be x. In brackets, we have factorizing x from this. The common factor here is x. So factorizing x, we have from x squared, we'll be left with x. And then from minus x, we'll be left with minus 1. All right. And then for this, positive 3x and minus 3, the common factor here is 3. So we're going to have positive 3 and then x minus 1 equals 0. So this is going to give us x plus 3 equals 0, x plus 3 equals 0, or we have x minus 1 equals 0. So our final answer now by factorization will be x equals minus 3 or x equals 1. All right. So this point here, x is actually minus 3 or 1. But then we are looking for the position at what points, all right, on the line. So since we are increasing and this is positive 3, if from year to year is a positive number, it simply means we cannot have minus 3 in between because this is like our zero end. 0, 1, 2, keep on increasing. You cannot have year to now be minus 3. It doesn't make sense. Minus 3 is supposed to be before 0 on this other side. All right. So the number we are going to go with as a position of x is going to be 1. It makes more sense to say this is 1 because you'll be increasing 0, 0 0.5, 0 0.9, something like that, and then maybe 1, 1.5, and then you get to 3. So this point x is equal to 1. So the point where the charge or the electric field of the charge is 0 is x equals 1. So which one is our correct answer? Remember, from year to year is 1 meter. So we're going to say either 1 meter from positive q charge, or if we are looking at it from this other charge, we're going to have 3 minus 1, which is 2 meters, all right, from positive 4q. All right. So the point where the electric field of this charge and this charge is 0 is 1 meter from this, or we say 3 minus 1, which is 2. All right, 2 meters from this. Okay, so let's see which one is our correct answer here. For option A, we have 1 meter from positive 4q. No, from this point to this point here is not 1 meter. According to what we have, it's 3 minus x, and x is 1. So this is 2 meters from this. All right, and then option B says 1 meter from positive q charge. This is the correct answer. All right, because from year to year is 1 meter. From year to year is x, and x is equal to 1. All right, so our correct answer is 1 meter from this positive q charge. All right, 3 over 4 is out of the way. There's no such point. That's also out of the way. All right. It doesn't make sense. So the correct answer is 1 meter from positive Q charge. I hope this is clear enough. If you have any question on this, please feel free to drop your question as a comment and I'll drop a reply immediately. Now, the next thing we're going to be talking about is the electric potential. Now, the electric potential at a particular point in an electric field is the work done in moving a unit positive charge from infinity to a particular point in an electric field. It can also be defined as the work done per unit charge. Work done per unit charge. The symbol for electric potential is V and it is measured in volts. Now, when we talk about electric potential, is the work done in moving a unit positive charge from infinity. All right, so we are looking at from infinity to a particular point. You can say this is the point P in an electric field. Work done in moving a charge from infinity to a particular point in an electric field, that's what we refer to as electric potential. All right, I will say it can also be defined as work done per unit charge. Don't forget the symbol is V, and then electric potential is measured in volts. So mathematically, we can have the electric potential is equal to work done over charge. This is our equation for electric potential. Now, electric potential and electric potential difference, they are similar, but they are not exactly the same. Now, when we talk about electric potential, is the work done in moving a unit charge from infinity to a particular point in an electric field. Now, electric potential difference or potential difference is the work done in moving a charge from one point to another in a conductor. All right. So if we have this to be a conductor, the potential difference is going to be between 2 points. Point A, we can say point A, and then point B, not from infinity to a particular point. Electric potential looks at from infinity to a particular point in the electric field, but then potential difference looks at the difference in potential between 2 points. So potential difference is the work done in moving a unit charge from one point to another. All right, we have the 2 points to be defined from one point to another in an electric field. That is what we refer to as potential difference. Potential difference also has the unit to be V, all right, or electric potential difference also. The unit is V, and then it is measured in volts as well, just like the electric potential. All right, and they also have similar equations for calculation. All right, this is also very, very important. Though we are going to look at potential difference in details when we get to current electricity. Now, coming back to our electric potential, we say the unit is work done all over charge. And we know from mechanics that work done is equal to force times distance. So rather than writing work done over charge, we can replace this to be V equals, rather than writing just work done, we can say force times distance all over charge. We represent our distance with R. So work done will be force times distance all over charge. So our electric potential is now going to be force, all right, times the distance over charge. Now, do not forget electric force, all right, or the force between point charges based on Coulomb's law is K Q1 Q2 over R squared. So the whole of this will be replaced with this formula. All right, we want to get another very important equation we're going to use whenever we have questions on electric potential. So that's what we're trying to do here. So we're going to have V equals, we have, instead of writing F, we can write K Q1 Q2 over R squared. So we have K Q1 Q2 all over R squared times distance all over charge. All right. Now, do not forget, when we talk about electric potential, we're looking at the work done in moving a unit positive charge. That's just one charge. All right. So in this case, we are going to be dealing with one charge. So it simply means this charge is going to cancel out one of these. All right. So we just have KQ, not Q1 and Q2, just KQ, just one charge. Now for the distance too, From our equation, they're also going to cancel out. We have R here cancelling out one of this. So our equation now for electric potential is going to be, we're going to have V equals KQ all over R. So this is one very, very important equation as long as electric potential is concerned. We have electric potential equals KQ over R, or you can also use this equation, electric potential equals work done over charge. So these two equations, all right, are very, very important as long as electric potential is concerned. So you can take them down, you can write them down. They are very, very important. K is still a constant, which is 9 times 10 raised to the power 9, all right, which is the same thing as what we had under electric field intensity. So please, these equations I'm giving to you, they are very important. The equation I gave to you for electric field intensity, which is E equals force over charge, is very important. Please take it down. Also, we have E equals KQ over R squared. Very important. Please take it down. Now we are looking at electric potential, work done over charge. Very important. Electric potential, work KQ over R. Very important. All right. So these equations are very, very important. You need to have them at your fingertips because they'll come in handy whenever you have questions that have to do with any of this. So now we are going to see how we can use these equations for electric potential to solve problems. So this question here, they said a charge 6 times 10 raised to the power minus 19 coulomb is in an electric field. Calculate the electric potential at a point 1.5 meters from the charge. So they gave us the magnitude of the charge to be 6 times 10 raised to the power of minus 19 coulomb. In an electric field, they say calculate the electric potential at a point. So we have the distance, all right, 1.5 meter, at a point 1.5 meter from the charge. So this is our distance. So we're looking at electric potential V. We want to calculate this, and we're looking at it in relation to Q and R. Now our equation, whenever we have electric potential with respect to distance, will be electric potential equals KQ all over R. KQ over R. So this is the equation whenever we have electric potential with respect to distance. The other one we have is V equals W over Q. We cannot use this here because we are not given the work done. All right. What we were given is distance. So this is what we are going to go with. All right. So now let's plug in our values. We have V equals, everything is in their standard units. Distance is in meters, so we can just go on to solve. So K, do not forget, is a constant. It is equal to 9 times 10 raised to the power 9 times Q. Q is equal to 6 times 10 raised to the power minus 19. So we have 6 times 10 raised to the power of minus 19 all over, the distance is 1.5 meters. So we have all over 1.5. All right. So at this point, we just use our calculator to simplify, and then we get our answer. So for the numerator, we have 9 times 10 raised to the power 9. So you can arrange your numerator again in brackets divided by your denominator. So open a bracket, and then we have 9 times 10 raised to the power of 9. All right. Times, we have 6 times 10 raised to the power of minus 19. Then we'll close our bracket, divided by, open bracket, 1.5, close bracket, and then you get your answer, which is 6. So our answer here is 6 volts. All right. So this is the value for the electric potential of this charge. Now the next question here says a 5 joules of work is done in moving 0.025 coulomb of positive charge from a point A to point B. What is the difference in potential at these points A and B? Do not forget, I said electric potential and electric potential difference, they are similar. When you talk about electric potential, you're looking at work done from infinity to a particular point in an electric field. Electric potential difference is work done between any 2 points in an electric field. They are similar and they have the same formula for solving them. All right. Now we are talking about potential difference, and they gave us W. The work done is 5 joules. in moving 0.025 coulomb of positive charge. So we have the charge given to us 0.025 coulombs. All right. So they said, what is the difference in potential? Difference in potential has the symbol V, just like electric potential. All right. So we have V. We're looking for V, and they gave us W and Q. Now the formula which relates this is V equals work done all over charge. All right. So to get V, we simply plug in our values. W is 5, and then Q is 0.025. So we have 5 divided by 0.025. So that will give us, we have 5 divided by 0.025. That will give us 200. So our V is equal to 200 volts, which is option B. Now our next question here says, consider a point charge plus Q placed at the origin and another point charge minus 2Q placed at a distance 9 meter from positive Q charge. So we have two charges, positive Q and minus 2Q. Minus 2Q is at a distance of 9 meters from this charge. So say this distance between them is 9 meter. They say determine the point between the two charges at which electric potential is 0. So again, at this point, or at a particular point between the two charges, electric potential is 0. Now, do we know the value of that point? No, we don't. So we'll just label it as X. That's what we're looking for. Determine the point between the two charges where the electric potential is 0. So since we don't know the point where the electric potential is 0, we label it as X. All right. So from this point to this point, electric potential of this charge is 0. Now from this point to this point, electric potential of this other charge is 0. All right. So now we try to separate them. We say for positive Q charge, let's try to calculate the potential. Now we know that our equation for potential, anytime we're looking at distance, all right, relationship between electric potential and distance is V equals KQ over R. We need to bring out this formula first. V is equals KQ all over R. So for this positive Q charge, our distance here from here to here is X. So for positive Q charge, we say electric potential will be equal to K, the magnitude of the charge is positive Q, which is still the same thing as Q, KQ all over R. Our distance from this charge to this point is X. All right. We're using this as our reference point because at this point, the potential of this is 0. Potential of this charge is 0. Potential of this charge is also 0. So it simply means the potential of the two of them are equal at this point. So let's get their individual potentials. We equate them and then we'll get the value of this point. All right. So we have V equals KQ for this charge. K, our charge, magnitude of charge is Q, all over the distance R from here to here, all right, is X. So our distance for this charge is X. So we have V equals KQ over X for this charge. Now for this other charge, for the minus 2Q charge, the potential will be V equals K. What's the magnitude of the charge? The magnitude of the charge here is 2Q. All right. We don't bother ourselves about this negative sign here because what we're looking for is just potential, and potential is a scalar quantity. It has only magnitude. All right. We're just concerned about the magnitude, not direction. So we ignore this negative sign. The negative sign here is just to tell you the direction of the force that will exist between them. This is a positive charge, this is a negative charge. You're going to have an attractive force. So they're going to be moving towards each other. So that's why we have a positive sign and a negative sign here, just to indicate the kind of force you're going to have. So moving on, we just concentrate on the magnitude of the charge, which here is 2Q. So we have K, KQ, according to our formula, V equals KQ over R. So we have K times Q here is 2Q. So we have K times 2Q all over R. That's the distance from here to here. All right, to this charge. Distance from here to here. Now, do not forget you're moving like this. So this is like a zero end. So you have 0, 1, 2, 3, 4. And then you have a number here. You keep on increasing. And then finally you have 9. All right. So from here to here, we said is x. So what will be the value from this point down to this point? Do not forget here to here is x, and from here to here, the total distance is 9. So this distance now will be 9 minus x. So we have this distance here to be 9 minus x. So we have kq, all right, which is the value of the charge. Our charge here is 2q, all right. So rather than writing kq over r, q here for this charge is 2q all over r. R for this charge now is 9 minus x, this distance. So we have 9 minus x. All right. So this is the value of this potential. But this is the value of the potential of this charge at this point x. So since this charge has a potential of 0 at this point, this charge also has a potential of 0 at this point. It simply means the both of them are equal at this point because both of them have potential at 0. So in that case, it simply means the whole of this at point x is equal to the whole of this at point x. So we just equate them since both of them have a potential of 0 at this point. So we have kq, all right, all over x, which is the potential of positive q charge, equals k times 2q, which is 2kq. We have 2kq all over 9 minus x. All right, which is the potential of this charge here. Now again, we have k and q appearing on both sides. All right, this is multiplying this, so this will cancel this will cancel this. The left is 1 here. All right, now you cannot cancel out the x because we have a minus sign. Whenever there's a plus sign or minus sign, you don't just cancel out. All right, you cross multiply and try to simplify. But if you have kq, which is k times q, all right, whenever it's multiplication, you can just cancel them out if they're exactly the same and appear on both sides of the equation. That's numerator, numerator, or denominator, denominator. So now moving on, we are left with 1 here on the left hand side for the numerator. We have 1 times 9 minus x. That will give us 9 minus x equals 2 times x. That will give us 2x. All right. So if we simplify further, we'll move minus x to this side of the equation. This is now going to be 9 equals 2x minus x to this side becomes plus x. So you have 2x plus x. That will give us 3x equals 9. All right. So to get x, we divide both sides by 3. So we have 3x all over 3 equals 9 all over 3. So this will cancel out this. And then you have x equals 9 divided by 3. That will give you 3 meters. So from this point to this point is 3 meters. So point x, all right, this charge, the point where this charge has a potential of 0, all right, on this line is 3 meters. All right, whereas from this other charge to this point, all right, we have potential to be 0. So this distance from this charge to this point, we are going to have 9 minus 3. All right, so for this charge is going to be 6 meters from this charge, potential is 0. So from here to here is 6, from here to here is 3. All right, so our correct answer here now is, they said determine the point between the two charges at which electric potential is 0. So we can say the points, all right, we can say the points where the potential is 0 is, we can say 3 meters from positive q charge, or we can say 6 meters from minus 2q charge. All right, from here to here is 9 minus x, and x is 3. So from here to here is going to be 6 meters. From here to here is going to be 3 meters. So for this question, it says 4 charges q1, q2, q3, and q4 are placed on points A, B, and C on the circumference of a circle of radius 2 cm. So first, let's sketch our circle. All right, so we have a circle, and then we have 4 charges placed around the circle. So we have, let's say this is point A, and this is point B, and then this is point C, then finally this is point D. So we have 4 charges placed around these points, or at these different points. So we have, can say charge 1, Q1, charge 2, Q2, we have Q3, then we have Q4. All right, they are placed on the circumference of a circle of radius 2 cm. So the radius of a circle is simply the distance from the center to any part on the circumference of the circle. So from here to this point, we can say is the radius. And they say the radius is 2 cm. So if the magnitude of each charge, so we have each charge to have magnitude of 6 microcoulomb. So it simply means Q1 has a magnitude of 6 microcoulomb, Q2 the same 6, Q3 6 microcoulomb, Q4 6 microcoulomb. So it simply means they are equal to each other. So we have Q1 equals Q2 equals Q3 equals Q4 equals 6 microcoulomb. All of them have magnitude of 6 microcoulomb. All right, now they said find the electric potential at the center of the circle. That's potential of each charge. All right, each of them at the circle. Potential of all of them together. That's to say potential of all of them combined at the center. All right, so to get the potential of all of them combined at the center, we need to get the potential of each individual charge. All right, since we are looking at potential and distance, we're going to use the equation V equals KQ all over R. They gave us Q for each charge, which is 6. They also gave us the distance. So if we want to calculate potential of this charge, we're going to use K times the magnitude of this charge, which is 6 microcoulomb, all over the distance of this charge to the center, since we're looking for potential at the center. All right, so we use distance to the center, which is 2 cm. Now you must convert your distance to meter. So we won't be using cm, we'll be using meter. So to convert from cm to meter, we'll say 2 all over 100, which is 0.02 meter. So this is what we are going to be using in our calculation. That's the distance we're going to be using in our calculation. All right, so let's start first with potential of this charge at the center. Potential of this charge at the center. Then we'll go to potential of this at the center, potential of this at the center, potential of this at the center. Then we'll add up everything and we'll get the total potential, which is what you're asked to look for. Potential of all of them combined at the center. So let's go ahead to solve this. So we have V equals, according to our formula, KQ over R. What's the magnitude of Q1? Q1 is 6 microcoulomb, all right? So remember, all of them have magnitude of 6. So we have 6 microcoulomb. So we have K is 9 times 10 raised to power 9 times Q, all right, which is this, times Q, which is 6 microcoulomb. We have 6 times 10 raised to power minus 6 all over the distance, which is 0.02. So if we use our calculator to simplify it, we're looking for the charge, we're looking for the potential of Q1. So we can label it as V1 actually. So we have V1 equals, using our calculator to simplify, we have, for numerator, we have 9 times 10 raised to the power of 9 times 6 times 10 raised to the power of minus 6 all over 0.02. So that will give us 2.7. So that will give us 2.7 times 10 raised to the power 6 volts. So this is the potential of just this charge to the center. So to get the potential of the second charge, V2. Now remember, V2 also have the magnitude of the charge to be 6 times 10 raised to the power of minus 6 coulomb, because they say Q1 is equal to Q2 equal to Q3 is equal to Q4. All of them have the same charge. They said if the magnitude of each charge is this. So V2 has magnitude of charge to be 6 microcoulombs. It also has its distance to the center to be 2 centimeter, which is 0.02 meter. So since the magnitude of the charge and the distance and even K, they are the same, it simply means V2 will also give us this answer. V2 is also equal to 2.7 times 10 raised to the power 6 volts. V3 will also be equal to 2.7 times 10 raised to the power 6 volts, because V3 being the potential of Q3, all right, will have its magnitude of charge Q3 to be the same, its distance to the center to be the same, because it's also radius. All right, distance of each charge to the center is the radius, which is 2 cm. Now V4 will also have its potential to be 2.7 times 10 raised to power what? 6 volts. Alright, so to get our final answer, which is the potential, alright, of all these charges at the center, we simply add this to this to this to this. So add V1 plus V2 plus V3 plus V4. Or we can simply say the potential at the center will just be the magnitude of one charge, which is 2.7 times 10 raised to power 6, alright, times 4. And that will give us the potential to be 1.08 times 10 raised to power 7 volts. So this is our answer. Now the next thing which we are going to look at is the relationship between electric field strength and electric potential. Now electric field strength, we know it to be E equals KQ all over R squared. Now this is still the same thing as electric field strength. E equals KQ all over R times 1 over R. We can just try to split our denominator. R times R is R squared. So the whole of this is still the same as this. KQ times 1 is KQ. R times R is R squared. Alright. Now looking at what we have here, you discover that the whole of this is simply electric potential, is V. Remember, V is equal to KQ over R. So rather than writing KQ over R, we can change this to V. So we're going to have electric field strength equals V electric potential times 1 over R. If we simplify this, we're going to have electric field strength to be equal to V times 1, which is V all over R. So this is the formula that connects electric field strength and electric field potential. This equation is very important and will come in handy whenever you're given a question that has electric field intensity, electric field potential, and distance. So this is the appropriate equation to go with. So at this point, we have come to the end of this lesson. Please make sure to subscribe and like this video and also share to your friends and your colleagues.